Bismillahirrahmanirrahim. Assalamu alaikum. I am Noorain and my group partner is Umar Mumtaz. The topic for our presentation is millimeter wave. Starting with millimeter waves, first of all, what are millimeter waves? Even with the advancement in 4G technology, the network is still running out of bandwidth. The 5G developer sought out a solution for a wider bandwidth, that is millimeter waves. Its data rate is expected to be 40 to 50 times faster, and wavelengths are between 10 millimeter and 1 millimeter, and band of spectrum between 30 gigahertz to 300 gigahertz. These are called as extremely high frequency. Why millimeter waves came into existence. In comparison, Wi-Fi currently uses frequencies in the range from 2.4 gigahertz, 5 gigahertz, and 6 gigahertz, while cellular network use 600 megahertz to 700 megahertz and 2.5 gigahertz to 3.7 gigahertz band. Although these band propagate further but support lower bandwidth. Due to less bandwidth, we have slow service and more dropped connections. As we can see in this picture, that in 2005 in a crowd there was only 1% who had a gadget, but advancement in technology in 2013 everybody was having one or more gadget. This is due to growing devices, and the other factor is growing demand, as we can see in this graph from 2013 to 2018. So why millimeter wave frequencies? First of all, it has efficient frequency reuse due to high attenuation, and more bandwidth is available at these frequencies. Millimeter wave spectrum is still undeveloped. So let's compare microwaves versus millimeter waves. Why millimeter waves were necessary when we have microwaves? First of all, frequency band of millimeter waves is 30 gigahertz to 3 gigahertz, and its bandwidth is ultra high as compared to microwaves. Also smaller due to short wavelength, while microwaves are large wavelength. As we can see, the peak rate of millimeter waves is 10 to 100 gigabits per second, while for microwaves it was for 1 to 5 gigabits per second. Application of millimeter waves are radar, millimeter wave imaging, medicine, and millimeter wave scanner, while the microwaves were used for radio and television broadcasting, telephony, satellite communication. Talking about the system architecture, and advanced RF transceiver architecture is needed with high integration level in chips to realize a millimeter wave using MIMO technologies. Basically, there are two system architectures for millimeter wave. Number one is the direct conversion architecture, and number two is the dual conversion architecture. Discussing them one by one, the direct conversion architecture is popular in gigahertz radio wave frequencies and can achieve compact and low power implementation. However, it gives rise to severe distortion such as LO feed through and phase lock loop. To overcome these above mentioned desired issues and to improve SNR, the dual conversion architecture came into existence. It is also called a sliding IF architecture. In this architecture, the demodulation and modulation working frequencies is slightly reduced, which makes the system more reliable. Therefore, the sliding IF architecture or dual conversion architecture is very popular in millimeter waves. So how does millimeter waves enable ultra fast broadband? Number one is spectrum, which is more spectrum 10x or more. Number two is large arrays and narrow beams, which gives us reduced interference, giving us better SNR, signal to noise ratio. And the other is spectrum reuse, that is multiple user can share the same channels. Observations about antenna in millimeter waves: large number of antennas used as base station and mobile station, as we can see in this figure, that 64 to 256 elements at base station and 4 to 32 elements at mobile user or user equipment. And directionality pattern changes. It depends upon physical layer signal processing, mobility management, and interference management. So, talking about the characteristics, millimeter wave communication suffer from huge propagation loss due to high carrier frequency. The rain attenuation and atmospheric absorption limit the range of millimeter wave. As you can see in the graph, that at light rate 2.5 millimeter per hour is its range, while at tropical rain, it is 100 millimeter per hour. These are also sensitive to blockage such as human and furniture and due to buildings and cell body blocking we can see in the figures below. So what are the existing solutions for these problems? First of all, to combat sphere propagation loss, beam forming is used. Basically, beam forming is a technique for shaping signal and in turning them into concentrating beam that are aimed at the receiver. So we can see in this figure that there is a base station and beam forming, elevation beam forming is used. The solution for rain attenuation is to use small cell sizes in order of 200 millimeter. Solution for blockage is a high density of infrastructure for building blockage, and for body and cell blockage we need rapid switching between line of sight and non-line of sight paths, and for hand blockage array diversity on the handset. So what are the key elements to enable millimeter waves in 5G technology? As we can see in the figure 2, there are basically two diagram. Number one is A is the sub 3 gigahertz system and the other is millimeter wave system. And sub in 3 gigahertz system there is a traditional cellular system. Beamforming is performed in baseband with the number of RF chains equal to the number of transmit antenna, while in millimeter wave system with a very small wavelength size we have large number of transmit antennas but with limited dedicated RF chains. There can be other possibilities such as modular antenna arrays where each beam stays on their own. So number second is the blockage effect. One possible approach to solve the blockage effects is through collection of non-line of sight communication. As we can see in this figure A, uh, where a line of sight breakage happens, the transmitter needs the receiver to quickly search through different direction for the non-line of sight signal to maintain the acceptable channel quality. And the other approach shown in figure B is to use the relays. Basically, relays are density deployed in urban areas such that whenever a line of sight beam blockage occurs and the collection of non-line of sight does not give the satisfactory channel quality, then our relays target at a nearby base station which can have a line of sight with the destination. Number third is millimeter wave transmission at D2D communication. D2D communication is basically device to device communication. The use of directional antennas in millimeter waves bring a narrow directive beam. We can exploit the millimeter waves into device to device communication. As we can see in our figure A, uh, a downlink millimeter wave transmission, which D2D pair 1, which is formed with a Q is uplink wave. We can still long as it avoid the main lobe of. In figure 2 we can see that q1 can still fulfill its convenience if a co-channel d to d pair is in communication, given that d to d communication is not steering at q1. Number fourth is millimeter wave transmission in homogeneous networks. In heterogeneous network, unlike homogeneous deployment in heterogeneous networks, there is a diverse set of base stations such as traditional macro base stations, the pico, femtos, and relays to enhance network capacity. In this figure, we can see a possible macro assisted small cell called phantom cell is placed, which establishes a new form of multi cell cross tier cooperation between macro and micro small cell for further network decentralization and spectrum extraction into higher frequency band. For this phantom cell approach with a C plane U plane split, there are no issues related to small cell cross tier interference. Due to this decontrolling signal due to handover between small cells and macro cells or among small cells can be significantly reduced. So now I would like my partner Umar Mumtaz to continue from here further.
Assalamu alaikum. The evolution of 5G. From this slide, we can see from the timeline of 2015 to 2020 how 5G has developed. Well, we started off in 2015 with macro based stations, which were increasing the frequency beyond 2.7 gigahertz to 6 gigahertz, thus increasing the bandwidth and increasing the efficiency as well. Moving on between the end of 2016 and majority of 2017, we had densification. In densification, what we did was we made smaller cells, DAS, LTU. Then moving on, in 2018, we had the massive MIMO and digital beamforming, which was up to 6 gigahertz. Array antenna was used, and in 2019 to 2020, and now we have 90 to 95 gigahertz, 70 to 85 gigahertz, 38 gigahertz, and 28 gigahertz millimeter waves. These are ultra wide bandwidth and ultra high throughput as well. Moving on, I'll discuss the advantages and disadvantages as well. The three principal characteristics of millimeter waves are the short length wavelengths, the large bandwidth, and interaction with atmospheric constituents. These characteristics translates into both advantages and disadvantages depending on the applications in mind. Further advantages: smaller wavelengths which allow to reduce component size, to achieve narrow beam width, to work in greater resolution. Moving on, wide bandwidths around main carrier frequencies that can provide a high information rate capability, wide band spread spectrum capability, high immunity to jamming and interference. Environmental interaction characteristics such as atmospheric attenuation and losses that are relatively low in the transmission windows compared to infrared and optical frequencies. Thus, lower attenuation in condition of dust, smoke, and battlefield contaminants compared to infrared and optical frequencies. With the millimeter wave large path loss feature, the interference can be relaxed and the frequency can be used by using small cell techniques as well as increasing the spectrum efficiency and communication capacity. Now I'll move on to the disadvantages. The smaller component size, thus increasing the need for greater precision in manufacturing, thus leads to greater costs. The narrow beam width, which can be a problem in target search and acquisition, thus millimeter waves are not suitable for large volume search. Smaller antennas which collect less energy in a receiving system, thereby reducing its sensitivity. The limited communication range due to atmospheric attenuation 10 to 20 kilometers, reduced range capabilities in adverse weather, poor foliage penetration, particularly in dense green foliage. Applications, I'll start with the first one, replacing interconnects on chips. Millimeter wave wireless will enable drastic changes to the form factors of today's computing and entertainment products. Multi-Gbps data links will allow memory devices and displays to be completely tetherless. Future computer hard drives may morph into personal memory cards and may become embedded in clothing as well. Information showers. By replacing copper wiring with massive bandwidth radio links that are located at building entrances, hallways, roadways, it will soon be possible to beam entire libraries of information to people as they walk or drive by. Future users of wireless devices will greatly benefit from the pervasive availability of massive bandwidths at millimeter wave frequencies. Multi-Gbps data transfers will enable a lifetime of content to be downloaded on the fly as users can walk and drive in their daily lives. The home and office of the future. The office of the future will replace wiring and wired ports with optical RF interconnections with both within a room and between rooms of a building as well. UWB relays and new distributed wireless memory devices will begin to replace books and computers as well. Hundreds of devices will be interconnected with wide bandwidth connections through millimeter wave radio connections using adaptive antennas that can quickly switch their beams. Vehicular applications are there as well. Millimeter wave is especially attractive for intra vehicle communications due to its inability to easily penetrate and interfere with other vehicular networks. High vehicle penetration losses are there as well. Vehicle to vehicle V2V communication may be used for collision avoidance or to exchange traffic information. Vehicle to infrastructure V2I links may also be used to communicate traffic information or to provide range and coverage extensions of mobile broadband networks. There are other applications outside the vehicle as illustrated in figure 1.18. The different applications of millimeter waves in vehicular applications including radar to vehicle communications and vehicle to infrastructure communications. Cellular and personal mobile communications. The key technological components are about to become mature to enable the multi-Gbps mobile data rates for future millimeter wave wireless networks using cellular radio architectures. Millimeter wave cellular networks may use 1 or 2 gigahertz channels, and by using time division duplexing TDD in a relatively small cell 200-meter radius scenario, end user data rates will easily be increased by a factor of 20 over most LTE networks, enabling multi Gbps mobile links for cell phone users. One of the applications includes aerospace as well. Different applications of millimeter wave in aircraft, including providing wireless connections for seatback entertainment systems and for wireless cellular and local area networking. Smart repeater and access points will enable backhaul, coverage, and selective traffic control. Moving on to the conclusion of our presentation. What we can see is that there is a data center. From there, wireless backhaul is used and millimeter waves DS is used. And then there is a BTS where multiple BS access for fewer handovers and high data rate. In between these are buildings which we cross over and line of sight links as well. From there on, we move on to the millimeter wave D2D and then to the non line of sight NLOS link. These are the, and moving further on, we have references which we have mentioned. These are the papers that we consulted in our presentation. Thank you.